Hi, guys. So today we're going to talk about Hess's law, which is you having to calculate heat of reaction or delta H or enthalpy, whatever you want to call it. But you're not given a potential energy diagram. You're not able to just say, okay, my products have this much energy, my reactants have this much energy. Let me subtract them and get my answer. Okay. So the first type of problem you're going to have to be able to do. So here they gave me a reaction, right? And they want to know what the delta H is. And then what they're going to do is they're going to give you other reactions, and you have to manipulate those reactions to create the reaction that's being asked about. So I know that's confusing. Let's look at the first reaction that they're giving me here. I have Pb plus Cl2 yields PbCl2. Now, if I go back up to my original reaction, I want PbCl2 to be on the left side of the arrow. I want it to be in the beginning, right? I'm trying to make these reactions look like the one that they're asking about. So what do I have to do to this reaction to get PbCl2 to be on the left side? I want to flip it over. I want to look at this reaction in reverse. So that's literally what I'm going to do. I'm going to take this reaction and I'm going to write it in reverse so that PbCl2 is on the left side. That's where I want it. Now, if you take a reaction and you reverse it, then you have to do something to the delta H. You have to reverse the sign of it. So going forward, this reaction was exothermic. It had a negative delta H. Now that I've reversed it, I want to make my delta H positive. Okay, so there I go. All right, now I want to look at my second reaction that's given, and I want to try to make this reaction look like the reaction that's being asked about. So I'm noticing that PbCl4 is on the right side, and PbCl4 is on the right side as well. So I don't have to do anything to this reaction. It's already in the right direction. So I'm just going to rewrite it. And I'm just going to start from here because I want my arrows to line up, and you'll see why in a minute. See how my two arrows are directly underneath each other? That's going to make the next part easier. PbCl4. And because I didn't do anything to the reaction, I'm going to keep its delta H the same. Okay. Now what I want to do is I want to add these reactions up. But before I do that, you want to compare what's on the left side of the arrow to what's on the right side of the arrow, and anything that they have in common you want to cancel out. So see how I have a Pb here and a Pb here? I can cancel those out. And see how I have a Cl2 here and two Cl2s on the bottom? I can cancel out one of those. So I'm left with no PbCl2s here. And if I'm getting rid of this 2, then I'm only left with one PbCl2 on this side. Now what you want to do is you want to add these equations together. Everything that's on the left side, you want to rewrite on the left side, but you want to do it together. And anything that's on the right side, I want to write on the right side. Does this reaction exactly match what is being asked? Yes. So once you've gotten the reaction to look exactly like the one that's being asked, you can now add up your delta H's to find the delta H of that reaction. Okay, and that negative sign, guys, that's important. You're adding a negative to a positive, so you're going to end up subtracting, but your calculator can do that for you. And when I do that, I get 30.1 kilojoules. And that's my answer. Okay. Another problem you guys might run into, let's look at the second one. Okay. So this is the reaction that I want, and I want to look at the two that are given to me. All right. So immediately I see that in this reaction, SO2 is in the beginning and I want SO2 to end up on the right side of the arrow. So I know from the example that we just did that I'm allowed to flip over reactions, right? I'm allowed to do that. Now, I'm also noticing something else. In the given reaction, I have two SO2s, but I only want to make one SO2. So not only are you guys allowed to flip reactions, but you're also allowed to change the number of moles and you're allowed to change the coefficients. So not only do I want to flip this reaction over, I want to cut everything in half. So I'm going to start with SO3 instead of two SO3. And I'm going to make one SO2 instead of two SO2s. And I'm going to make a half a mole of oxygen instead of a whole mole of oxygen. So how is that going to affect my delta H? Not only do I have to flip the sign because I flipped the reaction, but I want to take that 196 and I want to cut it in half. Whatever you did to your coefficients, you also have to do to your delta H. Okay, now let's look at my second reaction. Okay, in my second reaction, I want S and O on the left because I have S and O on the left, and I want SO3 on the right because I want it to cancel out with this SO3 right here. So it looks like I don't have to flip it around. The next thing I want to do is I want to look at those numbers. So guys, in the reaction given to me, there's two S's, but in the reaction that I'm trying to create, there's only one S. So again, if the given reaction is double the reaction that I really want, I want to change the coefficients so that they match up. So again, I'm going to cut this reaction in half, but this time I'm not going to flip it around. So I'm going to have one S instead of two S's. I'm going to have 1.5 oxygens instead of 3 oxygens. And I'm going to create one SO3 instead of two SO3s. So I didn't flip this reaction around, so the delta H is going to keep its negative sign, but I'm going to take 790 and cut it in half, and I'm going to get 395. Now, before I go ahead and solve this, I want to do my crossing out to make sure I did this correctly. So SO3 cancels with SO3. This half of an oxygen cancels with this half of an oxygen. So what am I left with? I'm left with S plus O2 on this side, and I'm left with SO2 on this side. So does that reaction match what's being asked exactly? Yes. So that's how I know I did this right. If you add up your delta H's, you're going to get negative 297 kilojoules. Okay, I'm going to give you guys one of these to try on your own. All right. How else could we be asked to solve for delta H? So this time, again, we're given a reaction, but instead of being given different reactions to like make into this reaction, we're given the heats of formation for everything in the reaction. So heat of formation has a symbol that looks like this, and it's defined as the heat change when 1 mole of a compound forms from its elements. Okay, so it's important for you guys to know too. So you'd have to be given the heats of formation for all the compounds in the reaction. There's no way of you knowing that or memorizing that. What you do have to memorize is that for elements, so for things that are not compounds, for things that are alone, the heat of formation is 0. Okay, so what your formula is, if you want to find heat of reaction, you're going to want to do the sum of the delta H's of the products minus the sum of the delta H's of the reactants. Okay. So sometimes it's kind of easier to label everything you have. So I'm going to go ahead and start labeling. Negative 393 is this carbon dioxide. Negative 285 is my water. Negative 104 is my propane. Oxygen is an element. Even though it's diatomic, it's still an element. So that heat of formation is going to be 0. All right. So here's what I have to do. Delta H. My products are the things on this side. Heat of formation is for 1 mole of that substance. So if it has a coefficient in front of it, you have to multiply it by that coefficient. Okay? So I'm going to do 3 carbon dioxides plus 4 waters minus. Now I'm going to look at my reactant side. I have 1 propane plus 5 oxygens. Okay. I want you guys to calculate this just to make sure you're putting it in your calculator correctly. I would try not to do it all in one step because it'll require a lot of parentheses in the correct spots. But when you do calculate it, you get negative 2215. Okay, if you did not get that, then we can talk about it tomorrow. But as long as you understand the setup, that's good. All right, now the last possible way you could be asked to find heat of reaction is using bond energy, and this is probably the most frustrating way because you have to know what kinds of bonds are in all of your compounds before you can do a question like this. So you have to draw everything out, and I'll do that with you. Propane is a little annoying, but we remember that carbon can bond in 4 spaces. So as long as every carbon has 4 dashes attached to it, it's all filled up. Oxygen is a double bond. And we have, it's going to be easier for me to draw this so you see where it's coming from. We have 5 of them. All right. Carbon dioxide looks like this. And I have 3 of them. You'll see why I'm doing all of this, I promise. And then last but not least, we have water. And we have 4 of them. And here's my last water. Okay, so as far as calculating delta H goes, if it's a bond energy type of question, and again, you'd have to be given this chart, the amount of energy to break a bond. You wouldn't have to know any of this. You want to do the opposite. You want to do the sum of the bonds broken minus the sum of the bonds formed. Now, if we think about where bonds are broken on the reactant side, and bonds are formed on the product side. So we're subtracting in the opposite direction here, okay? So let's take a look at what we have. Delta H equals, okay. The first bond I see, if I look at propane, I'm going to change my color so that you can see me counting here to red, okay? I have 1, 2, 3, 4, 5, 6, 7, 8. I have 4 bonds, single bonds between a C and an H. I'm sorry, 8. 1, 2, 3, 4, 5, 6, 7, 8, right? So I have 8 of those. And I have 1, 2. So I have 2 bonds between C's, and I have in my carbon dioxides, I have a double bond between C and O. Be careful because you need to pay attention to the type of bond it is too. And I have 1, 2, 3, 4, 5, 6 of those. So you see how drawing out the picture helps, yes? Okay. 498. Oh, I'm sorry, guys. Look what I did. I'm counting the carbon dioxide, which is on the wrong side of the equation. Ignore me. Erase that, please. We should be looking at the oxygen, the double oxygen bonds. I knew I was doing something wrong. Because, yeah, look. Right now, I'm only looking at the reactant side of the equation. So I have 2 oxygens connected by a double bond, and I have 1, 2, 3, 4, 5 of them. 5. Okay. So let's do that. I have 8 times 413 plus I have 2 times 347 plus I have 5 times 498. So that's my reactant side. Okay, minus. Now I'm going to do my product side. So I'll change to a different color again. Let's do green. Okay, so now I want to do my C and O bond, guys. So I'm just going to color over this. I have 1, 2, 3, 4, 5, 6 C double O bonds. And in water, I have bonds between H and O. I have an HO single bond. So I want to find that on my chart. Here's a single bond between H and O. And I want to count 1, 2, 3, 4, 5, 6, 7, 8. I have 8 of them. So on this side, I'm going to have 6 times 805 plus 8 times 464. Okay, so it's time consuming. It's time consuming. This is probably the worst one, I'm going to say. All right, please put this in your calculator. When you do and you get an answer, you should get negative 2054. And if your setup is correct and you're getting the wrong answer, we could just talk about how you're putting it in your calculator. All right, so we're going to spend a lot of time on these 3 formulas in class. Please come with questions tomorrow if you have any.